We're just going to do as many different things you can do with derivatives as we can. So I'm going to start off with this version of 14. And then I'm going to look at how to find the equation of a tangent line and some other things, all involving derivative of space curves being used in various ways. And this particular question, number 14, on my version of it at least, you're going to be finding the first derivative at 0, the unit tangent line at 0, the second derivative at 0, and a cross product. And keep the question there, and that way I can maybe do as much as I can here. So if you want to find the derivative, remember Calc 1 and chain rule. So it's e to the 4t times 4. It's e to the negative 3t times negative 3, and it's a 1. And if you want to find the first derivative at 0, you basically go 4e to the nothing, just 4, negative 3e to the nothing, just negative 3, and 1 is still 1. Now, if you want to find the unit tangent, what you need to do is, and since we're only being asked to find it at 0, I don't need to do the generalized version. I can just use this vector. So I'm going to find its magnitude, which is 16 add 9 add 1, which I believe is the square root of 26. And so the unit tangent vector is basically this guy, the magnitude, 1 over the magnitude of that vector. So it's 1/26 of these guys. So it's 4 over the square root of 26, negative 3 over the square root of 26, and 1 over the square root of 26. So that's your unit tangent vector. And what else are we to do? Second derivative. Right, now I know they're asking for the second derivative at 0, but to get the second derivative, don't we have to take this derivative first and then put in the 0, right? So sometimes you have to do, algebra before you can do number crunching. So if you differentiate this one, right, with respect to t, you get 4e to the 4t times another 4, so you get 16. You get negative 3e to the negative 3t times another negative 3, so that gets you plus. And you differentiate this guy, you get 0. And now I can calculate the second derivative at 0. In this case, 16e to the nothing gets you 16, 9e to the nothing gets you 9, and 0 gets you 0. Do you see how in this question, I had to deal with t's before I could get the second derivative? But for the unit tangent vector, couldn't I just use the numbers directly? I didn't need to do, the magnitude in terms of t and then, do the general version of capital T of t. Because they're only being asked one value, I kind of skipped that step. But for this fella, you had to do it. And then you finish with a cross product. And these two, we can use that guy and that guy. So we're going to find the cross product of 4, negative 3, 1 with 16, 9, 0. So I can do it with numbers. So it's I, j, k, 4, negative 3, 1, 16, 9, 0. And the answer is going to be so many i's, take away so many j's, plus so many k's. Okay, cover that guy up. Nothing take away 9 gets me negative 9. Middle one, nothing take away 16 gets me negative 16. The key one, 36 take away 48. 36 take away 48, negative 12. So we get negative 9 plus 16, negative 12. and we are done.
Wouldn't it be plus the 48 on the last one for K? Because it's minus a negative.
I should do that. It is, oh yeah, 36, add 48. Oh, that's actually easier to do. 80, 86, 8 and 6. I believe it's 84. Let me check it. I'm doing it in my head, always dangerous. 36 and 48, 84. Okay, we're good. And it just shows you how easy it is, especially if you're in a hurry to screw up things like subtracting a negative as an add. Well, that it basically was a version of question 14. So now we're going to look at how do you find the equation of a tangent line? And there's a number of these questions. Let's see what they are. So questions 15, 16 want to find the equation of a tangent line. Is that it? Yeah, okay. So I'll just pick one of these to do the job. Pick my own version then. Suppose I wanted to know the equation of the tangent line. That guy. And I'd like to know the equation of the tangent line when t was 1. Okay. So that's what our question is. This one's sort of alike. Was it question 15, but sort of alike anyway. So if I want to find the equation of a line, tangent line in this case, I need in 3D, I need two pieces of information. Don't I need to know a point on that line? And I need to know the direction vector. Right? That's how you find things in 3D. So the point on the line, which I'm going to call P, I'm going to get that by plugging in 1 here. So it's 3 times 1 squared, which is 3. 2 squared root of 1 is 2. And 1 squared 2 squared is nothing. And e to the thing, oh, it's 3, 2, 1. So the coordinates of P are 3, 2, and 1. These are called position vectors, but position vectors are essentially coordinates, right? They're almost interchangeable. So I've got half of what I need. Don't I now just need to know a direction vector? Well, in the good old, Calc 1 days, don't you just differentiate and plug in the point, right, and get the slope? But in this world, the direction vector comes from the derivative. And the first derivative in this case is 6t. If I call that t a half and I multiply it, can you trust me that you get 1 over square root of t? And while you're not trusting me and checking, I will move on. And if you differentiate this guy, you'll get e to the t squared take away t times the derivative of t squared take away t, which is 2t take away 1. And since I want to know the direction vector, I'm trying to find the derivative at 1. And that's going to be 6 times 1, which is 6. 1 over that is 1. And 2 times 1 is still 2. Take away 1 is 1. 1. So there is our direction vector. Right, so to get the point, t equals 1. Coordinates. To find the direction, derivative, t equals 1. Now you put them together, and basically, I think I call them ABC, don't I, in previous days. And this guy, I'm going to call it x1, x2, x3. So, well, that's called R, so I don't know what I'm going to call this guy. I'm going to call him S. So the equation of the tangent line S of t is 3 plus 6t, 2 plus 1t, and 1 plus 1t. And in WebAssign, it looks like this. So they don't use the little brackets, they use curved ones, which I'm a bit disappointed. And all you will write down is the red stuff. The brackets are already there. If you put in the brackets, any kind of bracket, because you didn't notice there were big brackets around this, WebAssign is going to say you're wrong. And a couple of you got your online test, you got 0 points, not because you did it wrong, but because you stuck brackets inside something that already had some brackets, right? So if it gives you a bracket, don't give it your own on top of that. Just a little hiccup, but if you're doing homework, it gets really frustrating if you do it right and you can't see any problem because there wasn't a problem, it was just how you wrote it in. And that causes issues. Are we good with how you find the equation of a tangent line? You only get a couple examples. It's homework, and that's similar. The other one has a little added issue, but only a little added issue. You're not told the value of t. You're going to have to figure it out. So here's x. Here's y. And here's z. And you're told that the point is that guy. Now that actually superficially looks like, well, that's great. I don't even need to find p, they're telling me. The problem with it is that, aren't you going to have to differentiate this? Right, it's going to look like this, right? And when you differentiate it, don't you need to know the t value to get the direction vector? So this point corresponds to what value of t? So what value of t would you have to put in here to make this happen?
T equals 0.
Yep. Want to tell us where you figured that out from? You're right.
I just looked at the z because it had the least amount of terms and it's 1. So to get e equal to 1, you have to take it to the 0 power.
Right. See, perfect. That's exactly what you did. So, I mean, if it works for that one, it has to work for the other two. The question's not fair, right? So pick the simplest as a good strategy. So far, so good. Right. So scanning on, we are now going to consider, what are we going to consider? Oh, I just made a mistake, not a big mistake. But 17 is also equation of a tangent line. So let's move on to 18. $19. Check if there's another one. $20. Right, for 18, 19, and 20, we're going to find an angle theta, which is the intersection of two curves. So I want you to imagine you've got a space curve, we'll call it R of t. And you've got a second space curve, call it, say, S of t. And they intersect at that point. If you zoomed in on that point, it would look, if you zoomed in enough, wouldn't it look like that? Wouldn't it look like two straight guys meet? And we are being asked to find the angle that they intersect at. And the angle they intersect at is the smaller of the two. Right, so if that's 80 degrees, that would be the other. Well, if that was 10 degrees, that would be 150. So that's the guy that we are after. So I guess the strategy is, how are we going to find the angle theta, which is the angle in which two curves that intersect at a point, what angle that is, right? How do we find it? Matthew?
Do you essentially just do the There was like an angly thing for vectors. I don't remember the specifics of that, but you do
Mhm.
that for the two derivatives at that intersection point.
So you find the derivative, let's say the intersection point is at t equals 2, right? You find the derivative at 2, you find the derivative of 2. That will essentially tell you the direction vectors. And then the angle at which two vectors intersect is the guy you're looking for. So, yep, you nailed it. Even if you did have to call it the angle-y thing, the gist of what you said was bang on. Okay, so I'm picking one. I'm picking question 20 because it looks the worst of the three. You have a curve. Oh, that's how they're doing it. They're calling it R1 of t. So it's t, 5 take away t, and 48 plus t squared. And the second one, they're just calling it R2 of t. That makes my life. No, R2 of s, sorry. You need a different variable each time. Makes sense. So you have 8 take away s. S. I have to make my s's look significantly different, or they end up looking like 5s. You got this guy. And we are being asked to find the angle at which these two guys intersect. So the first thing we need to do is find the coordinates of intersection. We have to find that guy there, column P. In particular, don't we just need to know what T and S number make the two things coincide? Now, that does take a fair amount of time to do. And so I'm going to cheat a little bit and just get this guy to tell me what the number is. But we'll talk about how you would do it without going into the details of the minutiae of it. Okay. The point of intersection, according to them, is 1, 4, 49. And that happens when t equals 1, and it happens when s is equal to 7. So these two curves intersect at this point, and I'm telling you that's the point, and I'm also telling you what the t and the s are. So this is how you would find it. You'd match these two guys together. You'd match these two guys together. I'll call them equation 1 and equation 2. And then you'd solve a system of equations and you would find out that s was equal to 7 and t is 1. But actually, that's not going to work for this one. Let me check. Yeah, that's not going to work. So I'm going to match this one, and then I'm going to match that one. There. I'll call them equations 1 and 3. Right. If you replace this t with 8 minus s, you will get an equation with s's that you can then solve. And trust me, it works. The reason 1 and 2 doesn't work is if you try and solve for them, they disappear. Those two are perfect matches. So pick any two equations out of the 3, and if you can solve it, you've got your guy. So we'll assume that part is now done. So let's find the derivative. Here it's going to be 1 minus 1 and 2t. And the direction vector then at t equals 1 becomes 1, negative 1, 2. And I'll call that direction vector v1. We then find the second one, we find its derivative. And that's going to be negative 1 1 to s, and we're going to find its derivative at s equals 7, and that gets me -1, 1, and 14, and that's v2. So you have two equations, you figure out a way of solving them, and when you do, you'll find out that t equals 1, s equals 7, and there is your point of intersection. Right. Now, for the angle between them, I don't need that point anymore, actually. But I do need to know how they cross. Does anybody know a more proper name for the equation I am going to use to find angle theta?
I don't know the name of it, but isn't it
Okay.
The dot product equals
Yeah,
length of
that's
A,
the name
length
of
of B cosine theta?
It's the dot product, right? That's what I was after. So cosine of theta is the dot product divided by the magnitude. You remember that guy? Okay, so what we're looking at here, well, I guess I'll need to find the dot product, so I'll do that. So it's going to be 1, -1, 2, dot product with -1, 1, 14. And that's going to get me 1 times -1 plus -1 times 1 plus 2 times 14. 28 take away 2, I believe that's 26. The magnitude of V1 is the square root of 1 plus 1 plus 4, just the square root of 6. The magnitude of this direction vector is 1 plus 1 plus 196, which is the square root of 198. So the cosine of theta is dot product divided by that. Let's figure out what that fellow looks like. With 26 divided by the square root of 6 times the square root of 198, and that's about 0.754. And to get the missing angle, then I just need to do inverse cosine of the answer. And oh, I'm in radians. Oops. These types of questions typically are in degrees. So I'll do that again. Inverse cosine of 0.754. And we get an answer about 41.1 degrees. So as you can see, there are a fair amount of work. Solve the equation to get the point of intersection. The main reason for that wasn't to find the point, but to find out who t and s need to be to do that. Once I know what t is, I can find its derivative and plug in 1. I can find the other guy's derivative and plug in 7. I now have the two vectors, and essentially from that point onwards, it's dot product, magnitude, magnitude, plugged into that formula, angle. Pause here. How are we doing, guys? I know I'm going pretty fast, but hopefully you're still with me. Okay. And that's the end of that group of questions. How to find the angle at which two things intersect. And of course, there's little variations on a theme, but essentially that's the gist of how you do it. And the next group of questions.
Professor, can I still look at that paper, please?
Sure.
Thank you so much.
The next group of questions, 21, 22. Yeah, keep going. 23, 24. I should probably just say to the end. No.
Okay, thank you. I'm done with it.
You good? Right. The next group of 4 questions are all about integration. So I'm just going to pick one at random and do it. Yeah, this one looks as good as any. So question 24. We're being asked to integrate 6, 1 plus t squared. T e to the t squared. 5 square root of t dt. It shouldn't surprise you that you integrate one of these things by essentially integrating 3 different times. You integrate that guy, you integrate that guy, and you integrate that guy. Would you agree that makes sense based on what you do when you differentiate? Can you integrate a space curve? Right. You're going to get the really quick version of this. That guy is 6 inverse tans of t plus an unknown constant, which I'm going to call C1. What method would I use to do this question here?
U
Who
sub,
would I say again?
U substitution.
Yeah. Who would the U sub be in this middle one? U equals what?
T squared.
Agreed. So I believe you end up with 1/2 e to the t squared plus c2. Will you just trust me on that while people check me? But that's the answer. Now, how would you go about trying to integrate a square root? What would you kind of do before you think about integrating?
Change it to t to the half.
Right, so then you can use the power rule. And the power rule is add 1 to the power 3/2. Divide by 3/2 is the same as multiplying by 2/3. So I get 10/3 the square root of t cubed plus c3. And you can double check that, but hopefully I'm right. Okay, so integrate, integrate, integrate. Are we cool with it? Now, let's show you how you write that guy into WebAssembly. You are going to do 6 inverse tan of t I plus 1/2 e to the t squared j plus 10/3 square root of t cubed k plus c. And you notice c is a vector. And c is basically c1, c2, c3. Also, when you're doing WebAssembly, you probably already found out, isn't there a I in WebAssembly? It's under vectors. And you can't just do the letter I in the alphabet, right? Keyboard. You have to do that I, or else it'll just say you're wrong again. So it's more formatting, how you make WebAssembly understand you. Right, so IJKs looks like that.
How do we input the C? Because if it's a vector,
Oh, there
C
is,
is not
yeah,
C
I
is
think
not a-
there's a guy that looks like this. So just stick a C in the box. I'm going to show you that because I'm not I'm only 90% sure. I'm not 100% sure that what I just told you is true. So I'm going to go in. Oh, darn it, go away window, you're in the wrong place. And we will show you what that looks like. Here's a view. Bring it over here. Can I get student view? No,
What would the bold option within the vector palette, would that also work for C?
it might be. I'm going to, as I say, I'm not 100% sure what it is, but that might be the case, what you just said. Right now, I'm moving windows around like some kind of Tetris game. Okay, here goes. Right, I'll zoom over and we will find out. So there we are. Click on this fella. And what was that, question 24? Okay. Now I'm not going to type in the whole thing, it'd take too long, but I'm clicking on that. I'm going into vectors, and if I wanted to do it, now do you do the box and then the thing, or the thing in the box? Let's find out. C, cover it up, make it bold. There, that would be vector C. This guy, oops, to a lot of spaces, or this guy with a C. If it's really nice, won't it take either? Now, if you wanted to do the vectors that we're talking about here, click on vector. There's 2i. You see how you do in the I, J's and K's. Okay. That is, that's that. We're almost finished, but not quite. But that was a good question because I never thought about it. Okay.
You mentioned that there's a sensitivity to the I. Is there a sensitivity to all of them, like the J and the K? Or
Yeah,
is it just I?
all three of them. So if you want to do a sine TJ, you have to do it that way, right? The J.
Okay, thank you.
Last two questions. If I tell you that the derivative is 4t cubed, 6t to the 5, and 2 square root of t, and I ask you to find what the original space curve was, and I tell you that this guy here was 1, 1, 0. Find this guy being told this extra piece of information doing this. Now they've actually done all of this in terms of IJK, but you know I don't like IJK, so I'm using it as ours. How do you think I could approach solving this problem? I know what the derivative is, but I want to find the original function R of t.
Integrate it.
Say again?
Integrate.
Integrate, right. So if you integrate this guy, that hex that's a t, dt. If you integrate this guy, would you agree that you would get essentially that guy plus an unknown constant, right? So let's see what we get. If I integrate this function, 4t cubed, 6t to the 5, and 2 square root of t, what do I get? Integrate that guy and you will add 1 to the power, divide by the new power. Integrate this one, you'll add 1 to the power, divide by the new power. Right. And t to the half, 3 halves, 2/3, 4/3, square root of t cubed, plus c. Now you are telling me that, oh, I forgot to tell you, that R of 1 is this, right? Well, I know who R of t is. It's this function. Me personally, I would bring this inside and I'd call it t to the 4 plus c1, t to the 6 plus c2, and 4/3 t cubed. To me, it makes more sense to have it inside. Now, I know what R of 1 is. It's 1 to the 4 plus this guy. It's 1 to the 6 plus this guy. And it's 4/3 times this guy. And I also know that it's equal to 1, 1, 0. So if this is equal to that, doesn't that tell me who C1, C2, and C3 have to be in this particular example? Can you remember in Calc 2 doing a question like, if I told you the velocity, you could work backwards and find the original possession function? It's kind of like that. So if you match these together, doesn't that make C1 0? If you match these two together, it makes C2 0. And if you match these two together, it makes C3 -4/3. So the final answer is t to the 4 plus nothing, t to the 6 plus nothing, and 4/3, that guy, -4/3. And we're finished. We have found the original vector with this boundary condition. And 25 and 26 are essentially the same situation. Any questions? A lot to take in today.
Just one.
Yes.
Where did the negative 4/3 come from?
It came from me using this, that I had 4/3 plus C3 had to equal 0. And so C3 had to be -4/3.
Okay,
You
that makes
hope-
sense.
Right, that guy is 0. And if that guy is going to be 0, that means that I now know what this fella should be.
Thank you.
Well, let's get started on our second of 3 sections. Or 4 sections, I think. Section 13.3 is called arc length. I'm not sure what you can see, so let me close off my windows and back in again. It's very closely attuned to what you would do in Calc 2. Can you remember in Calc 2, one of the things you could do is find the length of an arc, and it was done by an integration formula. So if you can imagine, this is starting at t equals 0, and I'm traveling along this 3-dimensional space curve, and we'll have it actually from A to B. Then the arc length is the integral from A to B of the square root of, and I guess I should put in my space curve. Let's suppose my space curve is called f of t, g of t, h of t. Then it's going to be f dashed squared plus g dashed squared plus squeeze in h dashed squared. Finding the length of an arc in 3D space involves integrating from the start value of t to the finish value of t of this formula, right? The derivative of that guy squared plus the derivative of that guy squared plus the derivative of that guy squared. If you can think back to what you did in Calc 2, aren't integrals involving square roots horrible? They are never nice algebra, right? You're going to find 3 situations. One is the square root is going to be a number. So all of that is just going to end up being 14 or 17. That's pretty easy if that happens. Second one is that the thing inside the brackets is a perfect square. So it might be like that guy, right? Now that's good news as well, because aren't square roots of perfect squares going to cancel each other out? And then you've got an integral that's kind of nice, right? And that's pretty common. This is pretty rare, but it does happen. The third possibility is, let's see if I can make one happen here. It's easier to say than it is to do. Let's put the answer and then work backwards. That you're going to get an integral that looks like that. Right? It's not a perfect square, but you can pull out a t to the 4. And it then becomes this guy. Why is this integral much easier to deal with than this integral? How would you integrate something that looked like t squared, the square root of t cubed plus 2?
Set u equal to t cubed plus 2, so that way.
A u sub, agreed. Right? Numbers are really nice. Perfect squares are very common. Pretty rare, but it might happen once, that kind of situation. So hopefully these are going to be your go-to guys, right? I guess there's a fourth possibility, which they better not have, because I tried not to make it a question. Do you know, remember in Calc 2, there was a whole load of tables at the back where it would tell you what the square root of 1 plus t squared is and all those guys, and you just had to go and look for it because nobody knew how to do it, you know, from scratch or didn't want to. I guess that's the fourth possibility. If by accident we get one of them, will you tell me and I will kill that question so we don't get one of them? Because you don't really have very good access to the back of a book, right? If you're going to do that, they might as well just tell you what the integral was, right? Oh, by the way, the integral of 1 plus t squared is, and do it that way. So I think we've got time to do one. So here it goes. We have a space curve. It's a helix, 9t, 3 cosine of t, 3 sine of t. And we're being asked to find its arc length from t is -5 to t is +5. So the arc length will be the integral from a to b. The first component's derivative squared, which is this guy, added to the second component's derivative squared, which is that guy, added to the third one's derivative squared, which is that one. So it's going to be from -5 to +5, the square root of, if you differentiate that, you get 9 squared. If you differentiate this guy, you get -3 sine t, but then you square it. And if you differentiate this guy, you get 3 cosine t and you square it, which is why you want helixes, because something really nice is about to happen. 9 squared is 81. This guy is +9 squared t, and this guy is +9 cos squared t. Can anybody see a nice identity for those two guys? You may have said it, but I didn't catch it. What's 9 squared plus cos squared the same as?
9 sine squared plus 9 cosine squared would be 9.
Yeah, a sine squared plus a cos squared gets you 1, so 9 of them gets you 9. So you are now looking at the square of 81 plus 9, which is 90. And integrating numbers is easy. You just stick a t at the end and you evaluate it at -5 and t is +5. And eventually you'll get 10 of those guys. And that can become 3 root 10. So you get 30 root 10, and it is. It's the right answer. So that would fall under the category of you got a number inside your square root. You're likely, not guaranteed, but you're likely to get a number when you have a helix. Helixes are sines and cosines with some kind of linear combination, right? So that could be 2t minus 1. And you can switch them anywhere you like. You just get a, and this particular helix is going to spiral along the x-axis. I know that because this guy doesn't have the sine or cosine. If this fella was in the middle, it would the helix would spiral along the y-axis. And if these were sines and cosines and that guy was 9t, it would spiral up the z-axis. So helixes are like corkscrews, right? They either go x, y, or z axes, depending on where this term is. And this term, as long as it's linear, right, 2t plus 4, you are going to get a really nice square root of a number. And those are the easiest ones to do. And I'm glad we picked that one. So put your last name down and bye-bye for now. And I will see you tomorrow, where we are going to be focusing on as many examples as we can of arc length. And then later on tomorrow, we'll do curvature.